Kijk. Per linea.
Ja, 2, 3.
Okay.
Good morning, everyone. We have the great honor to have today Professor Thorne, one of the most famous physicists in today's research, scientific research. And I'll say a few words to introduce his career. He got his Bachelor of Science at the California Institute of Technology in 1962. In 1965, he obtained a PhD in Princeton University and immediately moved back to his original school, Caltech, and he is there still then. And of course, that he was visiting a lot of other universities in the States and all over the world. His career is related to Einstein theory about relativity, and his knowledge brought him in to collaborate with the team searching for gravitational waves. And despite the fact that a lot of people didn't believe that will be found these gravitational waves, they did. And Professor Thorne was a mentor of the experiment, and his advice was key factors in the success of this experiment. During his career, he served as members in many committees, scientific committees or science policy committees. He obtained a lot of awards, honorary degrees from various universities. I'm not going to read, I have the list here, but it's too long and I don't want to take time from the seminar. But I want to mention, as I did yesterday, one of the awards was a film award. He was scientific advisor for a famous movie, Interstellar, which contributed a lot to attract young generation to science, and also for contribute to help physicists to understand what is about this relativity theory. So we are very honored to have you here. Welcome, and please make the presentation, and after that will be questions.
Okay. Thank you very much. So I'm going to begin by describing what it was we discovered with our gravitational wave detectors, and then I will go back and give you a little bit of history of how we got there. So 1.3 billion years ago, here on Earth, multicell life was just forming and spreading around the world. But in a galaxy, as Carl Sagan would say, far, far away. Two black holes circled around and around each other. This is what they would have looked like to your eyes if you had been there, based on a computer simulation. You have a uniform field of stars in the distance, and gravitational lensing, the bending of light rays around these black holes by their space-time curvature and their gravity, causes the patterns that you see. And as the black holes go around, you see very interesting patterns, such as this Einstein ring, which is the image of a caustic on the structure of the light rays that are going from your eye back to the distant stars. As the black holes went around and around each other, they emitted gravitational waves, losing energy, and so the black holes spiraled together, and then in a great collision, they produced a very strong burst of gravitational waves. How strong, I'll describe in a moment. But those waves traveled out from the galaxy in which the black holes lived, enter intergalactic space, across the reaches of intergalactic space, up to the outer edges of our Milky Way galaxy, where they arrived 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. I find it quite startling to think about what was going on as these waves traveled. They traveled onward for 50,000 years through our galaxy and arrived at Earth on 14 September of 2015. That's 3.5 years ago. They touched the Earth first at the Antarctic Peninsula. They traveled up through the Earth, unaffected by all the matter in the Earth, just penetrated freely through the Earth, and emerged from the Earth, traveling upward at the LIGO, or Laser Interferometer Gravitational Wave Observatory, at one of our detectors in Livingston, Louisiana, near New Orleans. 7 milliseconds later, they arrived coming up through the Earth at our second gravity wave detector in Hanford, Washington. They moved, stretched, and squeezed these gravitational wave detectors in a manner that I'll describe. And the signal came out through the instrumentation, through a computer, which had been, of course, pre-programmed to analyze any signal that came in. And that morning, the team that had built these gravitational wave detectors of 1,000 people, we were all amazed. It was too good to be true. In fact, it was so good that we suspected maybe this had been a signal that was artificially injected. It turned out not to be that. Or we wondered if somebody much smarter than us had hacked our computers. But it turned out not to be that. The instruments are so complex that there are 100,000 data channels come out of the instruments and the environment, each of them giving you information about things that might have gone wrong, monitoring aspects of the instrumentation. And so it took several months for the team to look very carefully at key data channels for any sign of anything that might be going wrong. There was no sign of anything that was going wrong. And so finally, the team, and we show a few of the members of the team here, which includes the LIGO team that built these detectors, but also a Virgo team in Europe that did not yet have a well-operating detector, but could participate in the data analysis. And the team then that is 1,000 people at something like 15 institutions plus Virgo, around the world, 15 nations, about 80 institutions around the world, analyzed the data then and agreed that this had to be the real thing. And so we announced the discovery on the 11th of February in 2016. It was front page headlines in all the major newspapers around the world, and even very tiny newspapers like Gold Beach, Oregon, where I have a home, a little tiny town. So it was a big deal. So how did we get here? And so that's what I want to talk about for you. It begins, of course, with Albert Einstein, who formulated his general theory of relativity, which tells us that space and time are warped, and that warping or curvature of space-time produces gravity, but produces a lot of other phenomena, such as gravitational waves. He formulated these laws in 1915, and then in 1916, just 100 years before we announced the discovery, he used his equations to predict gravitational waves. And what he described as gravitational waves are the following. If you have two inertial reference frames, one here and one there, and they're at rest with respect to each other, when the gravitational waves come through, they move the inertial reference frames back and forth relative to each other. So all you can have are local inertial frames in general relativity. You can't have global inertial frames because the space-time curvature moves them relative to each other. And so you can visualize this by putting particles at rest in these inertial frames, just a grid of particles out, say, in interplanetary space. And as the wave passes going into the screen, these particles are stretched in one direction, squeezed in the other direction in an oscillatory manner. And that pattern of stretching and squeezing can be described by a gravitational waveform, similar to the waveforms for sound that you can view on an oscilloscope, for example. And those gravitational waveforms are carrying information about the source, the pattern of stretching and squeezing. So Einstein, in his announcement of the prediction of gravitational waves, in that paper he says, not really strongly and explicitly, but when you read carefully what he says, he's basically saying that these waves are going to be so weak that humans will probably never be able to detect them. It was some 50 years, a half a century later roughly, that Joseph Weber at the University of Maryland embarked on an effort to detect gravitational waves. And the reason that he had the courage to do this, strongly encouraged and with a lot of discussion with John Wheeler, who was also my PhD advisor, was that by the time he came along, we knew of gravitational wave sources that Einstein never knew about that would be much stronger than anything Einstein knew about: black holes and neutron stars. In addition, there was new technology, computers, lasers, and so forth, that made possible types of gravitational wave detectors that Einstein never dreamed of. So it was a whole new world, both in terms of sources and in terms of technology, a half a century after Einstein's original prediction. So I was inspired by Joe Weber, also at Princeton, where I was a graduate student, by John Wheeler, who was my theory mentor, and Robert Dickey, from whom I learned a lot about experimental physics, although I'm a theorist. And so when I moved back to Caltech, I built a theory group working on black holes, neutron stars, and gravitational waves. And one of the things we did over the next few years is we began to develop a vision for the science that might be done with gravitational waves if you could detect them. So, let me describe the basis for that vision. It's the enormous contrast between electromagnetic waves and gravitational waves. Of course, all of astronomy, or almost all of astronomy, is based on electromagnetic waves. Before LIGO came along, a small amount on neutrinos and cosmic rays. But electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. Gravitational waves are oscillations in the shape of space, and also, if you look at it more carefully, under certain circumstances, in the rate of flow of time, themselves, oscillations in the fabric, in some sense, of space and time. Extremely different physical phenomena. Electromagnetic waves are, in astronomy, they're almost always incoherent superpositions of emission from individual atoms, molecules, or fundamental particles. Whereas gravitational waves are emitted coherently by the motion of, well, this says matter. The more up-to-date version of that slide, this is an older version, should say of mass and energy. There's no matter in the black holes, but the things we saw were colliding black holes. It was the energy that's tied up in the space-time curvature that was doing the radiating. So the bulk coherent motion of large amounts of energy or mass. Electromagnetic waves are all too easily absorbed and scattered as they travel from their source to Earth. So we can see only something like 10% of what's out there, out to the distances that we ought to be able to see because of obscuration, mostly by dust in interstellar space. Whereas gravitational waves are never significantly absorbed or scattered, not even if they're emitted in the Planck era when space and time were being born at the beginning of the universe, in the Big Bang. And so with these enormous differences, it's clear, first of all, that many gravitational wave sources won't even be seen electromagnetically because these two types of radiation are so different in these waves. And that's the case. We've seen no electromagnetic emission from the colliding black holes that we have seen. And that when it was clear to us in 1972, as we were beginning to develop a vision, that there were bound to be huge surprises that came out with gravitational waves, that we had the potential to revolutionize our understanding of the universe. And so that was why, by 1972, I had decided that if it appeared to me likely that the experimental effort to detect gravitational waves could succeed, I would do everything that I and my students and my postdocs could do to help the experimenters pull it off, help them make this be a big success. Simultaneous with our developing a vision for gravitational wave astronomy, Ray Weiss, whom I had known at Princeton, he was a postdoc with Bob Dickey, the experimental physicist from whom I learned so much about experiment. He was a postdoc in that group while I was a graduate student. Ray went to MIT, I went to Caltech, and simultaneous with our developing this vision, Ray conceived an idea for a new type of gravitational wave detector. What he said is you take 4 mirrors, you hang them from overhead supports. This is what it looks like looking down. And so one mirror here, one mirror there, hanging from overhead supports, one down here and one over there. When the gravitational wave comes along, oscillating at frequencies high compared to the 1 hertz swinging frequency of the mirrors. So the mirrors at those frequencies, say 100 hertz, behave just like free masses. They're pushed apart while these are pushed together. These are pushed apart while those are pushed together. And so the natural technique to monitor that, those changing differences in these mirror separations, we regard this as one arm of an interferometer. This is the other arm. The changing difference in arm length is laser interferometry. And so Ray proposed a scheme where the light comes into a beam splitter, is split in half. It goes through a hole in this mirror, bounces back and forth many times, and then returns back through the hole. And similarly here, returns back and interferes with the beam splitter. And so as one arm increases its length while the other one shortens, there's a shift in the wave fronts coming back to the beam splitter. And so a oscillation of the intensity of the light going toward a photodetector down here at the bottom. So the photodetector signal is a rise and fall that is a precise replica of the gravitational waveform of stretching and squeezing by the gravitational wave. I was in the process of writing a textbook on general relativity called Gravitation with my PhD mentor, John Wheeler, and Charles Misner. We were within weeks of sending the final manuscript to the publisher for publication. And I heard of this idea. I had not yet had a chance to study Ray's technical paper on this, nor to talk to Ray. But just looking at some numbers, it was obvious that this would never succeed. And so in the textbook, I wrote one sentence about this technique and said it is not promising. And that was an understatement of my view at the time. And let me explain why. So the predicted strain produced by the gravitational wave, the fractional change in separation of the mirrors as they're being pushed back and forth, delta L, the change in the separation divided by the separation L, was predicted to be about 10 to the minus 21 for the sources that we were thinking about at the time. That turned out to be actually the strength of the signal that we actually saw was 10 to the minus 21. Already in the 1970s, we knew about how strong the waves were, and that's quite remarkable. It's so early we thought we knew, and we were right on. That meant that if these mirrors are separated by, say, 4 kilometers, which is what we ultimately did in LIGO, that the delta L would be about 10 to the minus 17 meters. And let me remind you of how small that is. Even for a technical audience, I think it's good to go through this. You begin with 1 centimeter, divide by 100, you get the thickness of a human hair. Divide by 100, you get the wavelength of the light that's being used. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the mirror motions that we were expecting. That's approximately what's 10 to the minus 11, nearly 10 to the minus 12 of the wavelength of the light. To imagine you could split a fringe to a part in 10 to the 12 was incredible. I mean, I just couldn't believe that this would ever be possible. And so I said this was not promising. I then had long discussions with Ray and with Vladimir Braginsky, whom I will return to several times in this talk, a superb experimental physicist in Moscow, Russia. And I was already building a collaboration on research between Braginsky's group and my group across the Iron Curtain in this era of the Cold War. It was a very fruitful collaboration. And Braginsky came to be one of the most influential scientists working on LIGO from Moscow and transferring technology from Moscow to the US without the Russian government even knowing this was going on. After those discussions, I became convinced that this had a possibility, a significant possibility to succeed if we worked hard enough and long enough. And so I then turned my research group, to a large fraction of its effort, to supporting this experimental effort. Let me give you just one little example of why I became convinced. So if you imagine the light going back and forth, making 100 bounces, or 100 round trips in here, then the signal that we were looking for, which is 10 to the minus 17 meter motion of the mirrors, by 100 round trips, has been built up by a factor of 100. So it's 10 to the minus 15 meter effective signal by all those bounces. If you ask about the photon shot noise, due to the randomness in arrival of the photons at the photodetector, if you're really clever, you're dealing, of course, with the randomness in the intensity of laser light, which has a Poisson distribution for the photon arrivals, and the RMS fluctuations correspond then to being able to measure things to the wavelength of the light divided by 2 pi and 1 over the square root of the number of photons that you have available to you. So if you have, say, a 10-watt laser, then in a period of a gravitational wave, which would be, say, 100th of a second, you have about 10 to the 18 photons. And so if you take the square root of 10 to the 18 photons, you've then got 10 to the minus 9, 10 to the minus 7 meter for the wavelength divided by 2 pi. That's 10 to the minus 16 meters for the a limit on what you can, of where the shot noise would be, 10 to the minus 15 meters for the signal. You've got a signal-to-noise ratio of 10. But to actually do this, to get down to that level of precision that's governed by the photon shot noise in the laser itself, was going to be extremely hard. But those are the kinds of numbers that we went through for all the noise sources you could imagine. And Ray Weiss, actually, in his technical paper, he identified all the major noise sources that the initial LIGO detectors would have to face. One after another, he described how you might deal with these, and he made an estimate then of the sensitivity that could be achieved and showed that it was plausible that you could achieve the required sensitivity. This remarkable paper is really one of the most powerful and convincing papers I've ever read. He didn't publish it in normal literature. He put it in an internal MIT report series and then distributed it to friends. And why didn't he publish it? Because he thought that it would not be proper to publish something like this until after he had discovered gravitational waves. And so he learned differently fairly quickly and began to publish in the regular literature. So very quickly, other groups picked up on Ray Weiss's idea and began to build interferometers of this sort. A group at the Max Planck Institute in Garching, Germany, led by Heinz Billing, built a gravitational wave detector of this sort. And these are the bounces of the laser light on the mirror, just running around in a circular pattern in one of the Munich or Garching group's first experiments. In Glasgow, Scotland, Ron Drever conceived what turned out to be a better way to do this: operate each arm of the gravitational wave detector as a Fabry-Perot cavity. So the separation between the mirrors is the round trip of the light back and forth is an integral number of wavelengths of light, so light can be resonantly trapped between the mirrors. Then you don't need a hole here. You just have highly reflecting dielectric surfaces here, layers of dielectric that produce a very highly reflecting mirror on the inside faces and are reflecting coating on the outside face here. Light comes through and then it gets trapped between the two mirrors. and resonates back and forth. And it leaks in, gets trapped, and then gradually leaks out again. And this was much harder to make work technically, but it made an instrument that was far more versatile and capable of a far larger number of bounces back and forth. And so if it could be pulled off successfully, it really was the way to go, and it is the way that we did go. So having been convinced that this had a chance to succeed, I convinced Caltech that we should build such a gravitational wave group working on these techniques at Caltech. We brought Ron Drever from Glasgow to lead the effort. And at Caltech in 80 to 83, Ron and Stan Whitcomb, a new assistant professor, they built a 40-meter prototype, 1% of the length of the interferometer that we would actually in the end use. In the meantime, at MIT, the MIT group finished a 1.5-meter prototype, but more importantly, they, together with Stan Whitcomb, who was the second in command at Caltech, they carried out a detailed feasibility study in cooperation with industry, identifying all the major issues you would have to face for a construction of a real interferometer of kilometer scale. So a feasibility study for kilometer scale interferometers. In 1984, based on that MIT feasibility study and the prototype work at Garking, Glasgow, MIT, and Caltech, Caltech and MIT got together and to form a collaboration to create the LIGO project. It was led in 84 to 87 by Weiss, Drever, and me. This was the most dysfunctional leadership in the history of physics. We could not agree on anything very quickly. My job was to make the experimenters agree, but that was an impossible task. MIT was wanting to push in one direction, and Caltech in another direction. And ultimately, we were told, but it was absolutely obvious, you had to get a single director who had the authority to make final decisions, but would do so in consultation with the very best experts. So we brought in Robbie Vogt, who had been the first chief scientist at the Jet Propulsion Laboratory, which is the center out of which all the planetary missions for NASA operate. And JPL was created by Caltech and is a subsidiary of Caltech. So Robbie Vogt came on board. He knocked heads together between the Caltech and MIT teams, got them collaborating, and he led us in writing a superb proposal to construct a LIGO that went to the National Science Foundation in 1989. We said we would build facilities in which LIGO would be housed. Then we would do a two-step strategy. We would build initial gravity wave interferometers at a sensitivity where we would probably not see anything. But we would learn what the problems were that we hadn't anticipated. We would get experience with kilometer scale interferometers. And then we would build advanced interferometers at sensitivity where we should see lots of stuff. And so this two-step strategy was oriented towards success, and we didn't believe we could be confident of success unless we did it in this two-step way. It took 3 years to get approval. We got it fairly quickly with review committees and with NSF, but getting through Congress, because this was expensive enough, it had to be approved as a line item in the NSF budget by Congress. We were attacked by eminent astronomers who the culture of astronomy was absolutely that you don't build an instrument at a cost of hundreds of millions of dollars and fail to see anything and then build a second generation. They couldn't believe in that kind of a culture. Physicists, this was a natural way to go. But we were proposing to do astronomy with these instruments, and the astronomers said it is our right to judge you, and we believe this is not something you should be trying to do. You're not going to succeed. And so we fought a battle, a political battle for 3 years, and finally we succeeded in convincing Congress to move forward. But we told Congress, you've got to do 2 generations to have success. And Congress, from there on, 1992 to 2015, when we had our ultimate success for 23 years, Congress backed us year after year to within 10 or 15% the budgets that we asked for. No significant budget cuts, and following our plan step by step. And the Republicans and the Democrats both took great pleasure and pride in having supported this through that long period of 23 years until the ultimate success, a period where the total amount of money that was spent, taxpayer money in the U.S., was $1.1 billion by the time we were finished. When it came time to start construction, we changed directors. The superconducting supercollider, the SSC, was canceled by Congress. So we grabbed the most brilliant leader of large projects that I think that physics has ever seen, Barry Barish, who had been leading the design and construction of one of the two detectors at the SSC, and brought him into LIGO to take over. And he led us then in constructing the facilities. He expanded LIGO to include other institutions. The issue was that these instruments would be so complex it was impossible for Caltech and MIT alone to pull this off. And so he built the LIGO collaboration that is now 1,200 scientists and engineers in 100 institutions in 18 nations. And he figured out how to organize the collaboration with funding sources being different in other nations than at the NSF, but how to organize things so this would be a big success. And he led us in the construction and the first gravity wave searches with the initial interferometers. Then he was stolen away by the high energy physics community to lead the design study for the International Linear Collider. And we then had a succession of two other great directors, Jay Marks and David Wrightsey, as we then carried out our final searches with the initial interferometers, saw nothing, and then 2010 to 2015 we installed the advanced interferometers according to the plan we had laid out in 1989, and we're just ready to start searching for gravitational waves with the advanced interferometers. At that point, I'll show you noise sources. This is the strain noise, the square root of the spectral density, so in units of strain per root hertz, multiplied by the square root of frequency, and you get then the RMS noise in a bandwidth equal to frequency. The minimum of these noise curves is around 100 hertz. This number down here is a little below 10 to the minus 23, multiplied by the square root of 100, get 10 to the minus 22. The noise was at about 10 to the minus 22 for RMS noise when we began our searches with the advanced detectors. The first signal we saw was about 10 to the minus 21. It was actually a signal-noise ratio of 25, not just 10. There are lots of lines in this noise. This was the initial LIGO noise curve. This is the advanced LIGO noise curve in Hanford, Washington, and Livingston, Louisiana. The lines are just due to the vibrations of the wires by which the mirrors hang, or the wires by which, well, they're fused silica fibers now, by which the beam splitter hangs. So they're resonant noise, and you just remove those with a notch filter. It's very simple to remove those. And so you just ignore the lines in here, and this is what the noise looked like. So we had good sensitivity running from about 30 hertz up to about 300 hertz for the best sensitivity. Now, let me say something about black hole collisions, because this is what I expected in 1983 when we first proposed to build LIGO. This is what I thought would be the first thing we would discover, and it was. So we really knew where we were going. We weren't 100% sure, but we were pretty confident of where we were going. Though that was the likely first detection, and in 1983 we were estimated a strain for this gravity waves from black hole collisions of 10 to the minus 21. That's what the signal was. So that was what all of our proposals were based on as the most likely first source to be seen. The fundamental problem is that the collision of two black holes is very complex, and no techniques, no analytic techniques were known to solve Einstein's equations in order to predict the details of the signal. You could estimate roughly what the signal would be, but only roughly. The only way you could figure this out, because the collision is highly dynamical, there are no small parameters in which to do a perturbation theory expansion to compute the signal. the only way you could compute the signals was through numerical simulations, solving Einstein's equations on a computer. And so there was a great effort then. It had already been underway for a while, but under pressure from me, there was a great effort made to build the computer capabilities, the computer science capabilities to do these simulations. Things were not going well by the mid-1990s, and so Richard Isaacson, who was our superb program manager at NSF for LIGO, he contacted all the research groups in the world who were doing these simulations, said you've got to get together and talk to each other several times a year and start to coordinate between yourselves in order to pull this off successfully. So they created the Big Binary Black Hole Grand Challenge Alliance, it was called. And I was the chair of the advisory committee for the alliance and also reporting back to NSF because I knew where we needed to be. I was the one person who understood both the experiment and the theory. Richard Matzner was the leader of the alliance. He was at the University of Texas. And I became so concerned about this to try to push things forward. I had a long history of making bets with Stephen Hawking, so I made a bet with the young scientists working on the alliance. This is a list of them. That I wagered that LIGO will discover convincing gravitational waves from black hole collisions before the numerical relativity community has a code capable of computing the waveforms. I was hoping to lose this bet, but I made it hoping that that would help push them along further. By the early 2000s, I became extremely alarmed because they were still not able to simulate the orbital motion of two black holes around each other in one complete orbit, much less a collision of two black holes. And so it was really a big deal. I then left day-to-day involvement with LIGO to start a numerical relativity group at Caltech in order to do these simulations ourselves in collaboration with Saul Tucholsky's group at Cornell, which I thought was the best of the groups around the world that were doing it. But we at Caltech had the ability, well, both we had good, very excellent scientists, but we also had the ability to raise private money. NSF was not providing the funding for this that we felt was required. We felt you needed a medium-sized group of about 30 people, including graduate students, to pull this off successfully, and NSF didn't share that vision. And so in order to pull this off, we also raised private money from the Sherman Fairchild Foundation, which had supported Stephen Hawking's collaborative work with Caltech for many years. And Saul led this joint Caltech-Cornell collaboration, is now a joint professor between the two institutions. The first successful simulations of the orbital motion and final collision were carried out by one of our postdocs, Franz Pretorius, who on the basis of this very quickly became a full professor at Princeton University after he left my group. And by 2014, building on what he had achieved and lots of ideas from Saul and other members of the group, we were capable of carrying out simulations that were mature enough for LIGO's first observations, and several other research groups were also capable of that, but with much lower accuracy than our simulations and much longer compute times. So everything was ready, the instruments were ready, the simulations were ready. In 2015, I conceded the bet quite happily to the numerical relativity community. September 14, 2015, the plan was to start the first gravitational wave search on September 17. And the detectors were being brought into, they were being tuned, brought into the configuration that we thought would be best for the search when the first signal came in. David Wrightsey, the executive director of the LIGO collaboration, he declared our first such search has just begun 3 days early because we saw a signal. He froze the configuration of the detectors, and we were off and running. The first signal was, as I told you, it was really quite surprisingly good. It was strong enough you could see it in the raw data. So this is the signal, bandpass filtered to remove everything below 30 hertz and above 300 hertz, keeping only that region where the noise is low enough, or is maximally low. So a factor of 10 in frequency. And this is noise out here, and then the signal is coming in pretty obviously nice and strong. That's in Livingston, Louisiana. This is in Hanford, Washington. Once the signal was cleaned up, it was the gray area here in this plot of gravitational wave strain stretching along this up and squeezing down. So it's the gray area, it was the signal. And the best fit numerical relativity simulation, where you go in and you say, well, based on the numbers and the details here, it's pretty obviously from colliding black holes. Then the team doing the simulation, the SXS team, adjusted the masses of the black holes and adjusted their spins. So this had a low enough spin, it was seen edge face on, so the signal was not very sensitive to the spin. So it was primarily just the masses that were adjusted until we got the best fit, and that's the red trace that matches so beautifully the signal. And from that best fit, we inferred that the initial black holes were 29 solar masses and 36 solar masses for a total of 65 solar masses. The final black hole was 62 solar masses. 3 solar masses had been lost to gravitational waves. It's as though you had annihilated 3 suns and turned that all into gravitational wave energy and sent it off into the universe. The power output, because the signal lasted, that we saw for about 1/10 of a second, the power output is enormous. 3 solar masses in 1/10 of a second turns out to be 50 times higher than the luminosity of all the stars in the universe, the electromagnetic luminosity of all the stars in the universe put together. So 50 universe luminosities for 1/10 of a second, producing 3 solar masses of gravitational wave energy. No electromagnetic emission whatsoever, at a distance of 1.3 billion light years. We by now have seen 10 black hole collisions. These are just images from SXS simulations of the various collisions that we saw. Some big black holes, some small black holes, some beautiful music going on in the background to fit this. But it's just impressive to just watch these black holes go around each other and collide. The locations of the signals on the sky were very important because we needed to tell the electromagnetic astronomers where to look for a signal to see if there was anything there. And initially we had only the 2 LIGO detectors. And we determined the direction of the source primarily from the delay in the arrival time of the signal at various detectors. And with just 2 detectors, you can determine the direction of the source in one dimension, but not in the other dimension. And so the very first signal that came in was somewhere, this is the sky depicted as a sphere, somewhere inside here, a very large error box in one dimension, small in the other. The second and the third are up here. But a signal of black hole collision came in on the August 14, 2017, and it was localized in this very small region. It's about the size of the moon, a little larger than the size of the moon. And why were we suddenly so much better? We had one more detector. The Virgo team was building an advanced detector. They had built an initial detector. They were slower than LIGO getting the advanced detector operating. But by August of 2017, they were operating at good sensitivity. Virgo is 19 labs, a little more than 250 scientists at the time, France, Italy, Netherlands, Poland, and Hungary at that time. And with then 3 detectors, we could localize in the 2 dimensions by a delay time and arrival at the Earth. And so we really knew where we should send the electromagnetic astronomers to look. 3 days after that gravity wave signal came in, the signal came in from 2 neutron stars orbiting each other and colliding. Each neutron star 20 kilometers across, 1.5 solar masses, density at the center of the star, 10 times the density of an atomic nucleus. And the 2 neutron stars orbiting each other, emitting gravitational waves, spiraling together due to gravitational wave energy loss, collided and merged and produced a huge fireball of rapidly expanding, very hot nuclear matter, of course with falling density as it flew out, with opacity that gradually decreased, so that the first thing that was seen on Earth was gamma rays, the first thing that could penetrate this fireball, then X-rays, then ultraviolet, going on down through the electromagnetic spectrum. So the gravitational wave signal, depicted in a way I've not talked about, 1.7 seconds later, the gamma ray burst. The region where the gravitational wave signal came from on the sky was the green region. The gamma ray burst seen by the Fermi gamma ray satellite was inside this blue region, so not as good a sensitivity as the gravity wave detectors had. But then the UV, optical, infrared, and radio, you could localize to a particular galaxy down here inside this error box. And from detailed studies of the electromagnetic radiation, what we call multi-messenger astronomy now, gravitational waves and all these different electromagnetic wave windows or frequency bands. It was possible then to verify the prediction that had been made by theorists that a large fraction of all the precious metals, like gold and platinum, in the universe were created in neutron star collisions of this sort. So it was really quite startling. This was the most studied event in the history of astronomy. Something like 15 or 20% of all of the world's electromagnetic astronomers, plus the gravitational wave astronomers, plus neutrino astronomers, who in the end didn't see anything here, were looking and observing. And it was really a huge collaboration then in the end, a worldwide collaboration, and very exciting. So I want to just show you a few photographs of advanced LIGO, and then tell you a little bit of technical stuff before I quit. Okay, do I still have a little more time? I started a little late. That's okay? Okay. So this is advanced LIGO as seen from the air in Hanford, Washington. Down inside the corner station here, we have a vacuum tank in which one of the corner mirrors hangs, a vacuum tank that houses the beam splitter, a vacuum tank that houses the other corner mirror. Lots of seismic isolation because the motion of the ground, the ambient motion of the ground, just on a quiet day, is something like 1 billion times bigger than the motion of the mirrors that we're trying to measure. So a huge amount of seismic isolation in there, both active and passive. Barry Barish likes to put a baseball player there instead of a LIGO scientist to show you the size of the tanks. And this is one of the mirrors hanging from overhead support, a 40-kilogram mirror with a mirror coating on here, a dielectric mirror coating that gives rise to the colors when the light reflects off of there. But it's designed to, we use an infrared laser, and so it's designed to be highly reflective at the infrared wavelength of that laser. It looks like it's maybe held rigidly. It's not. It's hanging by fused silica fibers. But it's hanging with a surrounding cradle, so if there's an earthquake and a fiber breaks, it gets caught and doesn't fall to the earth. So among other reasons, that's why you have that kind of a structure there. As I told you, there are 100,000 data channels coming out of each instrument. That means the instruments are so complex that you don't know the personality of the instrument until you build it and start working with it. And so the advanced LIGO then, the instruments were operating during these searches at about 2.5 times worse sensitivity in terms of strain, amplitude of the waves, 2.5 times worse than our design sensitivity. And then the problem is to poke and prod the instrument in many, many different ways to figure out what's gone wrong and how to fix it, to bring it to design sensitivity. And that is what's going on. Advanced LIGO has now been shut down for 1.5 years for that purpose, learning the personality of the instruments, coaxing it toward design sensitivity. By 2020 or 2021, we expect to be there. And at that point, we'll see 2.5 times farther than we have been seeing That's a volume of the universe 2.5 cubed, or about 20 times greater. We have been seeing, when both detectors, well, now all three, including Virgo, were operating well simultaneously, a gravitational wave burst from collisions of two black holes. We're seeing those about once every 2 weeks. So at design sensitivity, we should see roughly 20 times higher frequency of signals, so about 1 a day. We now have plans and the approval from NSF, and the money is starting to come in for this, for a further improvement beyond advanced LIGO to get to 1.6 times better sensitivity in the early 2020s. So we'll be seeing black hole collisions a few per day. There are plans, but not yet a formal proposal to NSF for a much improved detector in the late 2020s that would bring black hole collisions in at 1 an hour. And then also plans in Europe for something called the Einstein telescope, in the US, something called Cosmic Explorer, that would increase by a factor of 10 the length of the arms. So a whole new facility to house these. And then be able to see 5 times further and see every black hole collision in the universe with masses below about 1,000 solar masses. And so it's really, as in other areas of electromagnetic astronomy, the prospects for huge improvements. What we may see with advanced LIGO and beyond, we should see gravitational waves from spinning neutron stars, from pulsars, black holes tearing neutron stars apart. We've already seen neutron star collisions, cores of supernova explosions, and huge surprises. So these are the kinds of things we're going after. And then just a few technical details, since this is a technical audience. A question that is always asked is, isn't the wavelength of light also stretched and squeezed? And so how can you ever see any signal? And it's absolutely true, the wavelength of light is stretched and squeezed by the gravitational wave. If you think about it, we're using each arm as a Fabry-Pro cavity, and if you have the light trapped in there, as the mirrors move back and forth, the number of wavelengths of light in here is an adiabatic invariant. And so the light stretches and squeezes along with the arms. So how do you deal with that? It's very simple. You use fresh light every half a gravity wave period, using one set of light when the arms are pushed apart, a different set of light when they're pushed together. So the light doesn't get a chance to be stretched and squeezed. You're continually putting fresh light in there. And that quickly and fully solves the problem. We want to make the light beam sensitive only to the motion of the center of mass of the mirrors, because that's what the gravity acts on, is on the center of mass. And how do you do that when the light beam is bouncing off of a face of a mirror that is made of individual atoms? They're a factor of 10 million times larger than the desired noise. And the atoms are vibrating thermally with amplitudes 1 million times larger than the desired noise. But there are a huge number of atoms inside the beam, and we make the beam pretty big, about this size at the mirrors. So you average over huge numbers of atoms. And the atomic vibrations are at 10 to the 13 hertz, the Debye frequency, whereas we're looking for gravitational waves at around 100 hertz. So you average over close to 1 trillion vibrations, thermal vibrations of the individual atoms. And so by averaging over space and time, you can get down to where you're really sensitive only to mirror center of mass motion, aside from some tiny residual in our frequency band, which we call thermal noise. And then the key thing is to understand that residual and keep pushing it down lower and lower. The biggest problem is from thermal noise in the dielectric coatings on the faces of the mirrors. And so that's where a huge amount of effort is now going in. Vladimir Virginsky told us many, many years ago that we would have to face up to the fact that the center of masses of our mirrors, or whatever kind of gravity wave detector that we are trying to use, are quantum mechanical. and they undergo quantum fluctuations. So we have a mirror now that behaves like a 40 kilogram particle, because we're sensitive only to the center of mass motions, aside from some tiny residual thermal noise. And a 40 kilogram particle has random quantum fluctuations in our frequency band that are just at the level of the advanced LIGO sensitivity. This, of course, is motions that are tiny compared to the random fluctuations of the position of an electron inside an atom. Those are 10 to the minus, those are about 1 angstrom fluctuations. These are far, far smaller fluctuations because our particle is far bigger. We're making measurements at a level that is so small compared to an individual atom that we are actually sensitive to the quantum fluctuations of the center of mass degree of freedom of our mirrors. And so in order to deal with that, where for the first time humans in LIGO see human-sized objects behave quantum mechanically, we've had to develop what Brzezinski conceived of and called quantum non-demolition technology. How do you get a gravitational wave signal through a 40 kilogram particle unscathed, with the signal not being demolished by the quantum behavior of the 40 kilogram particle? And that has been a major effort, joint effort between Brzezinski's group at Moscow University and my group at Caltech over a period of several decades. The technology for doing this is now in hand, and we're beginning to install it in LIGO as we speak for the next gravitational wave search. The key idea came from Carlton Caves, who was one of my graduate students in 1981. He said that what you need to know is that when the laser light fluctuates up and the beam is split in half at a beam splitter, the light goes up simultaneously in the two arms. So you're not very sensitive to fluctuations in the laser light coming off the laser. But if vacuum fluctuations, quantum electrodynamic vacuum fluctuations, come in the backward into the interferometer from the output port, they then are reflected in this direction and transmitted in that direction. And that process coming through this port produces antisymmetric fluctuations. So these vacuum fluctuations beat against the laser light to produce an increased intensity here, a decreased intensity there. And so that's where the gravity wave noise comes from. And what you have to control then is the vacuum fluctuations coming in this port beating against the laser light. And you can control those by a technique called squeezing, where you send the vacuum fluctuations through a nonlinear crystal that is being pumped by the laser. And you can modify the vacuum fluctuations of the light. Those vacuum fluctuations of the light then modified, through their radiation, when they beat against the laser light, they push against the mirrors and modify the quantum fluctuations of the center of mass motion of the mirrors. So that's how you do quantum non-demolition. You manipulate vacuum fluctuations coming in the output port in order to manipulate the mirror motions. It's very clever, but it has taken a lot of technology development to pull this off successfully. 15 years of QND technology development in LIGO being installed today as we speak. Another issue that Brzezinski pointed out to us is a terrible parametric instability. If the mirror vibrates, for example, in a quadrupolar motion, so this quadrant is coming out, that quadrant's coming out, this quadrant's going in, that quadrant's going in, then it will take the Gaussian beam of light and it will drive some of the light into parasitic modes that have a quadrupolar pattern. Those parasitic modes will beat against the Gaussian beam, producing light pressure with a quadrupolar pattern that drives the mirror to vibrate. And so you've got a real problem, that the mirror vibrations produce patterns in the light that drive the mirror vibrations. This becomes worse and worse as the power goes up. We want to operate with a megawatt of power in order to keep photon shot noise down. And we run into severe problems when we get up to around 200 kilowatts or of medical watt of circulating power inside the arms. When we get up to about 100 to 200 kilowatts, this becomes a killing process. So we've had to develop techniques to damp these mechanical vibrations, but we'll also, beginning with the next gravity wave search, we will lower the laser power at the cost of increasing the photon shot noise. Then we will reduce the photon shot noise by the technique of squeezing. So this just gives you some sense of the technology we have to deal with. I want to just finally remark that these LIGO and Virgo gravity wave detectors, they operate in a millisecond period gravitational waves, 10 milliseconds typically, so 100 oscillations per second. There is a planned ESA mission called LISA, in which you have 4 spacecraft that have proof masses that are protected from the solar wind and solar radiation, so that they move freely under the influence only of gravity, and then the spacecraft are shields against the surrounding noise. Those proof masses sitting down inside here are tracked, their motion relative to each other are tracked with laser beams in LISA. And this is a technique looking for gravitational waves that have wavelengths 10,000 times longer than LIGO's is looking at. So periods of oscillation of minutes to hours. So if you think of LIGO as being like optical astronomy, this is like radio astronomy. Then there's a technique that radio astronomers are pursuing called pulsar timing arrays that are looking for gravitational waves with periods of years to decades. A technique called polarization of the cosmic microwave background, looking for gravitational waves with periods of hundreds of millions to billions of years. By the 2030s, all 4 of these frequency bands will be successful, we're quite sure. And so it's as though you were turning on optical, radio, X-ray, and gamma ray detectors for the first time over a period of 20 years. We're doing that with gravitational waves. And so I'm going to quit at that point. I could talk a little bit about the science that we're expecting to do, but I think it's time for me to quit, and we'll have some discussion. I'll just say that the science is very exciting. We're exploring black holes in ways we never dreamed possible in the past. We will, by the 2030s and on into this century, begin to explore the birth of the universe, seeing gravitational waves from the Big Bang itself, seeing them amplified by inflation. So we'll be exploring observationally the Big Bang, the laws of quantum gravity that govern the Big Bang, convolved with the amplification effects of inflation. We'll be looking for gravitational waves with LISA that are coming from the phase transition in which the electroweak force came apart to create the electromagnetic force and the weak nuclear force, so the electroweak phase transition. So the birth of the fundamental forces we'll be observing when the universe was at an age of 10 to the minus 12 seconds. So this is really, for me, the most exciting part of this field, is going into the process of observing the first tiny fraction of a second of the universe's life and the processes that were going on then. And that's where we are going. I might just conclude by reminding you that it's 100 years since Galileo built his first little optical telescope, pointed at Jupiter, and discovered Jupiter's 4 largest moons, and thereby created modern electromagnetic astronomy. It's 3.5 years since LIGO turned on and saw collisions of black holes, gravitational waves from collisions of black holes, and created gravitational astronomy. These are the only 2 kinds of waves that can propagate across the universe, bringing us information about what's far away. So what the LIGO team has done, the superb LIGO team, was for gravitational waves what Galileo did for electromagnetic waves. That's why it's a big deal. And when you just think about the huge changes in our knowledge of the universe that have come from electromagnetic waves, then I'll let you imagine what we may get from gravitational waves over the next 400 years, working together with electromagnetic waves. It's really an exciting beginning for this new era of multi-messenger astronomy. Thanks. Thank you. Yes.
Thank you very much for coming here.
Thank you.
And we are greatly enchanted by this talk. And also, I ask you a favor. This is our book for
Yes.
myself and students. We work a lot of physics.
Yes.
And
It looks
not
well
all
used.
Talk is extraordinary,
Yeah, yeah.
but the book is extraordinary.
Yeah.
If nobody have seen it,
No.
it's absolutely extraordinary.
So there is a new edition. So if you have the old edition, you can buy the new edition. But the new edition is the only change that it has a long preface and a long introduction that describes what we think are the most important new discoveries about gravitation that were made since 1973 when we published this book,
Exactly.
together with references to where you can go learn about the new stuff. This book is very out of date in almost everything except the mathematical part. The mathematical part hasn't changed. We wrote this book at a time when relativity was the province of mathematicians, and physicists had not yet come to understand that relativity would be really important for physics and for astrophysics. And so it played, I think, a significant role in bringing relativity back from the province of mathematicians to physicists.
Yeah,
So
yeah.
thank you.
We enjoyed the physics from here,
Yeah.
and it's brilliant inside, like a book. And the ideas is also for teaching or for understanding and for history and for the mathematics, and a lot of bibliographies inside.
Yes.
May I have your autograph? on this book?
After we finish the question period. So in a minute.
Because
Yes,
it's
thank you.
absolutely great.
You keep it and give it to me again when.
Okay.
Yes, thank you.
Thank you very much.
Thank you. Thank you.
Questions?
Hi, I have a question about your question mark at the LIGO sources. In order to fit the gravitational wave signal, we need to know the waveform, so we need to know the source.
Well, so you can also, if you have a signal that lasts for a very large number of cycles, more than about 20 cycles, then you can dig deep into the noise if you know the waveform in advance. If it's less than about 20 cycles, you can find it even if you don't know the waveform in advance. And a great effort has been made by the very large data analysis team in LIGO and Virgo to develop techniques to pull signals with unknown waveforms out of the noisy data. And so it's really only long signals that you can do much, much better if you know the waveform in advance. And so the surprises will likely come either from deviations in the long waveforms, say from the in-spiral and collision of two black holes, deviations from general relativity if there are any, or from fairly short signals, less than about 20 cycles, that are of unknown origin initially. You see something and you just don't know what it is, and then you struggle to try to understand. Hopefully you see some associated electromagnetic emission or neutrino emission, and then it will take probably quite a while to figure out what's going on. But those are the two ways in which we expect surprises.
Thank you.
Hi. So my question is, how do they tell the difference between what kind of objects are colliding, if it's neutron stars or black holes? Because the neutron star has a radius of almost the Schwarzschild radius. So that's my question.
Yeah. So part of the answer is that neutron stars are less massive than black holes. So we have seen, as I said, 10 black hole collisions. The masses of the black holes that we have seen range from about 8 solar masses to about 80 solar masses, that factor of 10. The neutron stars are about 1.5 solar masses. there is a gap between the two at this point. If we see something around 3 solar masses, we won't know from the measured masses. So let me back up. You get the masses with highest accuracy from the in-spiral phase before they collide. And so from this in-spiral phase before they collide, you can get pretty good masses. You can thereby distinguish, unless it's the mass you're coming out with is somewhere around 3 solar masses, then you won't know. But the final merger waves will be different for the neutron stars than the black holes. But the merger waves are a high frequency where LIGO has a fairly large noise at the present time. And so when we start seeing something around 3 solar masses, we'll have a big push to reduce the noise at the higher frequencies. Remarkably, we have the capability to do that. We can take photons that are in the laser light that are being used to get good sensitivity at 100 hertz, and we can move those photons in the gravity wave frequency space up to, say, 1500 hertz, and thereby reduce the noise at 1500 hertz by adjusting the reflectivity and position of one of our mirrors. It's called a signal recycling mirror. So we have the capability to reconfigure the noise sources to go after and get good sensitivity on the final merger waveforms. So this is what I expect will happen as we get more and more data. We start seeing something where it may be hard to distinguish between the neutron stars and the black holes.
Can I have a follow-up? So can you calculate how far the objects are when they merge? So basically to calculate the sum of their radii? To figure out if it's...
Yeah, and so that's part of the merger signal. So even better, before they merge, they exert tidal forces on each other in the same way as the moon exerts a tidal force on the Earth and deforms the Earth, not just the Earth's ocean, but the Earth itself. And that tidal deformation of the neutron star becomes strong enough that it shows up in the very last piece of the in-spiral, and then the deviations become stronger and stronger as the merger starts to occur. And so, yes, this is a variant of what you just said. So that's part of the answer. But the problem, as I say, is that the LIGO noise is, that signal is going to be coming at frequencies between, say, 1,000 hertz and 3,000 hertz, where photon shot noise is a problem. And so in order to really dig in and see that part of the signal with good sensitivity, we've got to reduce the noise there, which we can do, as I said, by reconfiguring one of the mirrors in the detector.
I'm interested in two phenomena. First,
could you put it closer to the mouth?
First will be the superradiance of black holes, because that would be important for dark matter detection, light dark matter detection. And my question is when and if this could be provable by these such techniques. And the second one would be gravitational memory, shockwave gravitational memory, as it is important for the quantum information interpretation of gravity.
So the first question was, what about black holes?
Superradiance.
Okay. Let me just think. Let me talk about memory first, because this I'm more on top of. So the issue is the following. If I have two black holes that spiral together, collide, and merge, they send off gravitational waves in all directions. And those gravitational waves have energy, equivalent, they have mass. And so the waves that go off not toward us, but off, say, transverse to us more or less, they produce a gravitational field that, because this is two things now flying apart, that is different from the gravitational field that that mass had when it was one thing stuck together. So you've taken basically three solar masses and thrown it off in those directions. Three solar masses, mostly moving off to the side, produces a different static, unchanging gravitational force than three solar masses sitting together as part of the mass of the original binary. And so as a result, you get a waveform that oscillates, and then it settles down at a different height that is a different amount of stretch and squeeze than when you began. And this is what's called the memory. The memory is a measure then of the mass and motion of the gravitational waves that went in a different direction than toward us. The stuff that goes toward you doesn't contribute to the memory. Interestingly, this memory was first discovered by a mathematician who had been a postdoc of mine, Dimitris Christodoulou, a superb mathematician, but he talks a different language than we do. I spent an entire week staring at his technical papers in order to understand that this is what the memory is. It's just the gravitational field of the gravitational waves that didn't go toward you. This has, as you say, become an important issue for fundamental physics. It's related to the so-called information loss paradox. The memory, it's very hard to measure unchanging forces. They're subject to low-frequency noise. Low-frequency noise is a terrible problem. So what you do is you look for the beginning of this steady signal, but you can't build up signal over time because of so-called low-frequency noise. And that means it's really quite hard to find this memory effect. And the best way to find it has been devised by a set of people theorists who work in this field, I think one of them is Yuri Levin, who is now at Columbia University, who have said, you can take the data from large numbers of black hole collisions, and you can dig the memory out by combining the data from large numbers of black hole collisions. And in that way, I think there is real expectation of seeing this memory effect within the next decade, is my impression. But I've not looked really carefully at Yuri's and collaborators' papers on it. Your other question has to do with superradiance. Superradiance is the fact that if you have a rapidly spinning black hole, then there's a lot of energy in that spin. That energy can be extracted. So, for example, if you send, and this was Zeldovich in Moscow that first realized this, if you send an electromagnetic wave or a gravitational wave in from the outside, it can go in, it can scatter off the black hole, and it can extract energy, come off with more energy that went in by extracting spin energy of the black hole. This is what's called superradiance. And then there are various associated phenomena, and I am not aware of what the prospects are from seeing superradiant type effects with LIGO or with LISA. So I can't give you a good answer, but that's what the phenomenon is. Yeah.
Hi. So when you talked about the black hole merger signals that LIGO has seen, you said that there has been no electromagnetic follow-up as opposed to the neutron stars. So is this a general rule, you think? There's no chance of seeing an electromagnetic follow-up? Or so there is none, or is above the...
So nothing has been seen, but I think there is hope of seeing something. The issue is that if you have a single black hole, black holes are almost always, we think, surrounded by accretion disks that come either from just interstellar space or more likely from the black hole having tidally torn apart stars, and some of the material from the star that was torn apart by the black hole has gone into a disk. If you have a binary black hole, there should also be a disk around the binary black hole. But as the two black holes go around each other, the gravitational forces as they go around are going to push the gas out away from the binary. I don't know just how far. But the hope is that when the black holes merge, there's a sudden change in the gravitational forces, and that should disturb the disk around the black hole to some degree. And that's where you would get a electromagnetic signal associated with the gravitational wave merger. So there have been estimates made of the strengths of this, and there is hope of seeing electromagnetic signals then from the disturbance of the disk when the black holes merge, but nothing has been seen as yet.
How can we measure the speed of gravitational waves through black matter when through black matter when we don't even know the speed of light through black matter?
Well, we can measure the speed of compare the speed of gravitational waves and of light from the sources that we do see. So in particular, as a clear example, we had this neutron star collision, and from the gravitational waves, we could say when did the gravitational waves arrive at Earth that were produced at the moment the black holes collided, which should be when the fireball was created. And so from the gravitational wave shapes, we can say when did the gravitational waves arrive from the collision moment. And then we compare with the arrival of the first electromagnetic signal, which is gamma rays, and that was a 1.7 second delay, which is very plausible for the delay required for the fireball to become sufficiently transparent, low opacity to go down low enough for the gamma rays to get out. But it may be that, it may be something else causing the delay. It could be that light and gravitational waves propagate at different speeds. But we can say that that we have verified that the propagation speeds of the light and the gravitational waves are the same to an accuracy of 1.7 seconds, divided by the time it took for the entire signal to reach the Earth, which in this case is, I've forgotten the precise number, but something like 100 million years. And so 1.7 seconds, 100 million years is 10 to the 5, 10 to the 7, so 10 to the 12, about a part in a trillion, to about a part in 10 to the 12. The gamma rays and the gravitational waves are propagating at the same speed. So we may not know the precise speed itself, but we know that the speeds are the same. Because it should vary according to the material which it passes through. Let me just say that the gamma rays experience almost no dispersion except right at the source. That is, they are predicted to propagate at the vacuum speed of light. And the gravitational waves are also predicted to propagate at the vacuum speed of light. And so you have the two optimal things to compare in terms of stuff that you believe, according to the laws of physics, are propagating as close as possible to the vacuum speed of light.
Okay, you said about that mirror that vibrates in a pattern as a quadrupole. Do you do any active wavefront correction?
So those mirror vibrations, they don't influence the waveforms. What they do is they pump laser light energy into parasitic modes that increase the noise. And so they make the detector noisier, or can even drive the detector to stop operating because you've lost your laser light. They can drive the mirrors to vibrating this quadrupolar pattern, which causes noise, but it's not affecting the measured waveforms particularly. It's that basically the instrument becomes very noisy or stops operating at all.
So please comment a little bit about grand unified theories and the fact that gravitation is not still in the standard model. So that's one. And the second, please develop a little bit the fact that there is no synchronization between these gravitational waves detectors and the neutrino ones. So they have not taken a look at the same thing, or what is going on there?
So grand unified theories, I'm not smart enough to comment. Let me make a remark connected to this, which is more a sociological or psychological remark. I think these issues in fundamental physics, high energy physics, particle physics, are tremendously interesting and tremendously important. The issue of the nature of the laws of quantum gravity, which ties into gravity not being brought into the standard model, and tremendously important. But that's a crowded field. If I were working in that field, I'm not as smart as many other theorists. I wouldn't be able to do much. So I've had success by picking a field that was not crowded, where almost nobody was working on it, and focusing there. And that was gravitational waves. But I avoid crowded fields. That's also, I didn't confess this, but when I left LIGO in order to work on computer simulations of the sources, was partly because I was really worried the simulations weren't working. Was partly because I don't like crowded fields, and LIGO had become too crowded. And so the reason I don't work on this and don't know a lot except from talking to colleagues about grand unified theories is my choice to do things where I can have an impact when I'm not as smart as the best theorist. Okay. Your second question was something I could answer, and remind me what it was. Okay, neutrino. So it would have been plausible that we would have seen neutrinos from the neutron star collisions, except that the neutron star collisions were so far away that the neutrinos were too weak to be detectable. So we have to have a source that is closer than these neutron star collisions, the collision that we've seen. The ideal place where we're going to have combined neutrino and gravitational observations that are successful, I think, is in supernova explosions. Both neutrino detectors and gravitational wave detectors, according to our understanding of the emission from supernova explosions, and we have observational data from one supernova explosion for the neutrinos, nothing yet for gravitational waves. But they have about this capability of looking out to about the same distance, which is just the very nearest galaxies besides our own, because the signals, both neutrino and gravitational, are at a level where neither of us can see much beyond the immediate group of galaxies. And in that group of galaxies, supernova explosions are one every 10 years, 20, 30 years. And we have to hope that we see one. If the one that has been seen in nearby galaxies was supernova 1987A, LIGO was not operating then. That was 2 years before we proposed LIGO for construction. If we were to see another supernova 1987A, it would be tremendously exciting. We should see the gravitational waves. You should see the neutrinos. It's a mystery as to how the core of a star collapses. We know it forms a neutron star, and then somehow the collapse energy gets released into the outer envelope and drives the outer envelope off. But the details of that are not understood. The computer simulations seem to say it's very delicate. Depends very sensitively on unknown physics. And so we really need observational data of what's going on in the core of the supernova explosion in order to deduce what is the mechanism of explosion. And that's why it will be so exciting through a combination of neutrino observations coming off the core and gravitational wave observations for gravitational waves coming off the core to see the first supernova and for the first time probably really understand definitively what causes the explosion. Okay.
Now I propose you one more question because too many questions we have, so we cannot...
As a regular citizen, what we can do to support the scientific discovery in our country, let's say, in general, not only in our country?
Well, I think it's very important, if you talk about regular citizens who are not scientists or engineers, it's very important that the citizens be educated enough about science to understand what science can do and technology can do to make life better, and what problems are real problems and what are not real problems that have technological or scientific basis, and how can society work to solve them. And the obvious areas that are very controversial in the United States because of political ideology or religious beliefs are climate change and evolution. There is no doubt in the minds of the scientists that climate change is real, that humans are causing it, and that we have a huge problem. But this is not accepted by hardly anybody in the Republican Party, which controls Congress and the presidency over the last few years. So we have a huge problem in the US. The general population needs to understand science well enough to appreciate that this is a real problem and to appreciate that we have to develop technological answers that reduce global warming. And similarly, biotechnology, which has huge prospects for making life ever so much better for humanity, it really relies on the fundamental physical processes that go on in evolution. It relies on guided evolution for much of biotechnology. And if you have a citizenry that, for religious or other reasons, doesn't believe in evolution, you've got a problem in a democracy. And so these are the things that worry me the most. Things like the kind of science that I do, all you have to convince is a handful of powerful people, even in a democracy. We had to convince senators and representatives in the US Congress that they should support this, and we were able to do that. We didn't have to convince everybody in the population, though it helped that, that this became well known and was popular among regular citizens. Yeah. Okay.
Thank you very much.
Thank you.
Thank you. Now we are going to see the laser room and the control room, so if you like to join us,